Okay. I work for AT&T Labs in access part of the network, the last mile broadband, as well as the fronthaul for mobility. I'm going to be presenting today on a couple specs that AT&T started presenting the idea during the Global Summit this year. And I want to acknowledge my colleague, Mike Mesh, who started this and has been contributing the spec. So we've had several conversations within the community, and we've made some progress. There is a draft version of the specification for both the fronthaul gateway and the CAS called the Converged Access Switch out in the wiki. So I'm going to be today just going to be giving you a highlight of what we have out there so far. So let me kind of start with, for folks who are new to this presentation, kind of start with a high-level overview of how this white box fits into the mobility transport, right? So I'm kind of going to start with like our current architecture. So if you look at what we have in the LTE, primarily we have two modes, I would say, depending on the operator and your geographic location. Either you're going to have it distributed, meaning your base station and the radio are all in the same tower, and then you backhaul via Ethernet to your APC core, right? Or you could also have a centralized RAN, in which case the BBU is kind of, they call it BBU hoteling, is one term that they use, where the BBU is in a centralized location called a CRAN hub, and then you have, it's more typical for like a pico sites, and especially in a high dense area. So these are the kind of the architecture we have. And for the centralized, right, we typically use fiber, either direct fiber or WDM with colored optics. So those are kind of what we have today, present mode of operation. And also, the CPRE is the fronthaul protocol, which stands for, I guess, Common Public Radio Interface. That's a standardized protocol. So if you look at what's happening with O-RAN and in the future, in addition to what I call the centralized and the distributed RAN, now you have another layer of disaggregation. Because O-RAN is working on the DU-CU disaggregation, as well as putting it on a cloud, right? Virtualizing your CU, etc. So just depending on what type of architecture you pick, you could have different ways of deployment, I would say. You could do your CU-DU in the CRAN hub. So this is more of a centralized architecture, or CU and again DU split between a regional site and an edge location, right? Or you could do your DU more distributed, if that makes economical sense. So again, it's going to be depending on where you deploy, you're just going to have a mix of these architecture, right? And if you look at also the core side, the 5GC, same thing is happening, right? They are splitting the control plane and the user plane, and then the user plane is moving closer to the customer. So, I guess now you have, I would call it like a bunch of functions that could be placed in different location. And I'm sure there's going to be like a sweet spot where you want to be placed. And so my focus today is going to be on this, the circle, right? So between the RU and the DU. So that's the fronthaul piece, whether you do CPRE, with LTE, or eCPRE with the O-RAN specification. So that's going to be the function. And few things to keep in mind is when you talk about fronthaul, it's the latency. We have strict latency requirements for that link, normally within a 10-kilometer range. And then you want to be able to aggregate whether it's an LTE CPRE traffic or an eCPRE traffic. So aggregate multiple radios back to your DU. And also timing for 5G is also a critical one. So with that, so now I'm going to kind of talk through the use cases. So let's look at the centralized RAN, right? So this picture kind of shows the two white boxes. So one, you see the FHG, which is the fronthaul gateway, which is targeted to be at a cell site location, and it can also be in a CRAN hub, like in a CO. And then you have the CAS on the other side, so that is your aggregation. It's a large-scale aggregation to basically aggregate like multiple macros. Say, consider like 20 to 30 macros into this hub. You could have, meaning several tens to hundreds of macros, aggregated to a hub location. So this particular use case is talking about what we call the ROE, the Radio over Ethernet, and that's the IEEE 1914.3 standards. With this solution, it actually requires like it's like a paired solution, right? So you have this ROE mapper at your cell site, which will basically encapsulate the CPRE stream, the blue stream, encapsulate that into an Ethernet frame, and then at this location, you need to demap it back to the CPRE to go to the BBU, right? So this is pretty much like, still sort of like a one-to-one, so you will still go to your LTE BBU. Whereas the eCPRE, that can be front-ended to this ODU. And this is the architecture that's being worked in the ORAN. I'm not addressing, in my presentation, it's just for reference on how the CAS will interface with the ODU pool. So that's another effort going on. We would expect that to come into OCP probably, in the next few months or a year. So here, let me kind of talk a little bit about the ROE, right? So in ROE, you kind of have three modes of operation according to the standards. The first one is the tunneling mode, which is basically CPRE agnostic. So you don't do anything with your CPRE frame, simply encapsulate it, and there's pretty much no bandwidth savings. In fact, it will probably be a little bit more due to the header. The second one is the line code aware, where you can remove the line coding, 8B, 10B line coding, which is typically like 20% overhead. And I would say that would be your bandwidth saving for that. And then in the structure aware, so that's where you kind of get into the CPRE structure and look at your, they call it the antenna and the carrier containers, AXC containers. That's your, I guess, the IQ data. And then look at some unused containers and you're able to remove them. So that way you get a little bit more efficient in your bandwidth. If you look at CPRE, that's usually whether or not it uses it, you have to allocate the bandwidth, right? It's a constant bit rate. So that's why, meaning this is a kind of a faster, in our view, it's a faster time to market, but it's not, I wouldn't consider this to be our end goal for how we want to provide the solution, right? Simply because of the transport bandwidth it requires, as well as the need to do the ROE demapper at both sides, and you're still not able to go to your ODU architecture, right? So there are some disadvantages, but it's definitely a faster time to market. The second use case that we're looking at is what we call the lo-fi. So this is another function we expect the fronthaul gateway to provide. This is basically you're offloading the BBU, the lo-fi processing. So that's basically your lower, the physical layer. If you follow the ORAN, the 7.2x split, so in 5G, what they did is the lo-fi, the lower physical layer function is actually part of the radio. And the ODU would have your hi-fi or the high part and the MAC and the other upper stack, right? So in order to kind of, in order to be in sync with how the 5G radio is deployed, by offloading the BBU, so for example, the lo-fi is actually part of this BBU, right? By offloading a function of that into the fronthaul gateway, the lo-fi function here, now you're able to, so that basically it makes it equivalent to what a 5G radio will do. So that way you can enable the DU pooling at the CRAN hub. So you get to like a unified architecture, which would be your long-term architecture, at the DU side. And again, big savings on the fronthaul bandwidth as well. Why it's important? Because if you look at a macro site, typically you may have anywhere from, 15 to 20 LTE radios, depending on the market. And there are several CPRE rates as well, CPRE 3, 5, and 7. Meaning that they are different bandwidth, but if you look at CPRE 7, which is a 10G, you may be close to like 200 gigs. So that way, if you reduce this bandwidth, that's again, that equates to cost. And by using the white box, you can do gray optics instead of, if you do a DWDM with colored optics. So those are, a couple use cases that we're looking at. Again, talking about the latency, so you see the 125 microsecond round trip. So that's between the radio and the BBU. Okay, and this is a round trip. Like I said, it's about for a 10-kilometer radius. Round trip. So if you just look at the fiber, of 10 kilometer, that equates to about like 100 microseconds. I think it's like 5 per kilometer. And then so that kind of leaves us only 25 microseconds for all the hops. So we expect all of these switches to be pretty efficient, very low latency, 3 to 4 microseconds at the most. So I'm going to kind of go through some of the high-level spec. So these are, we have provided this in the specification document. Let me walk through the fronthaul gateway, right? So as I said, it is transporting packetized fronthaul for both CPRE and eCPRE. So that's at the cell sites, and be able to support ROE as well as the low-fi function. Those are the two kind of the critical functions that we expect the fronthaul gateway to perform. It should support the TSN. In the fronthaul gateway, it's a little bit more important because you could, in a Pico site, you could have a 25 gig. So we expect the TSN to be, more useful in a fronthaul gateway. So that way you're able to preempt the traffic and give it the priority compared to others. And also support Class C timing. For the fronthaul gateway, we have a couple proposals for the form factors. The first one is going to be the 1RU, the 24-port, 10 or 25 gig client ports, and then 400 gig network port. So that's the 100 gig that connects to the CAS in your central office or the CRAN hub. And then there is also another proposal for a outdoor hardened unit. Outdoor hardened unit, with 8 25 gig client port and 100 gig network uplink. So the deployment location for these are typically cell sites, especially for the outdoor hardened unit. It would be just the Pico site, pole mount, and then the 1RU could go in a cell site or in a central office. And all of these have to be NIPS compliant and meet the class 2, the temperature as well, the -40 to +65 C. And for the pole mount, it should be IP65 hardened unit, with a class 4. So it's a little bit higher temperature range. So this is pretty much like an enclosure. It does not go into any cabinet. That just needs to be mounted on a pole. For the higher, the bigger box, the 1U box, we're looking at an NPU capacity of 800 gig, with integrated traffic manager and packet processor, with an Intel x86 CPU, 4-core, and then the typical, hot swappable and redundant fans and power supply. We've looked at a few silicon, and for this, especially for the ROE support, we have the Broadcom's Monterey silicon supporting the ROE. But unfortunately, there is not an ASIC yet in the market to support the lo-fi. So that's where, a bulk of the work is going to be, at least in the next few months, trying to figure what is the optimal design. Right now, we are looking at some FPGA options to have this function. So basically offloading this into the FPGA, that's one solution. I guess, I think here I would say, we're still kind of work in progress. So appreciate, any feedback or other silicon options as well. On the converged access switch, so this is a bigger 100 gig box that goes into a CRAN hub or a cell site. So it's basically aggregating multiple cell sites, right? Our target is to do 20 to 30 macro sites using this box. So we're looking at port density of anywhere from 40 to 64. Obviously, more the ports, better. Be able to low latency as well as a non-blocking switching capacity, which kind of means you don't want it to be to have like big buffers on the switch silicon. Support TSN and Class C timing. TSN is kind of a question here. I know some of you may have thoughts. Why would you need it for 100 gig? Not very critical for if you look at a preemption case, but TSN we're looking at the standards. It's pretty broad. Some of the specifications that they have, it's primarily all of 802.1q, which is the standard Ethernet, with priority queuing. So all of those need to be supported, as well as we're looking at other, other requirements in the TSN as well. Again, in this one, these are going into central office, like I said, so it should have the NEBs, level 3 carrier grade, unlike your fronthaul gateway, which is more like, if you look at AT&T's previous design, I think which Janet presented last year, the cell site gateway router. So I would say in terms of environmentals, the fronthaul gateway is more like a cell site gateway router. And this CAS is actually closely resembles, I think, one of your DDCs, right? So here the important ones are the Class C timing and the TSN and the low latency. So one of the silicon that we have been looking at is the J2C from Broadcom, and there are also others available, Marvell, Mellanox, Tofino. They're also good option for this type of a switch. So in terms of form factor, we're looking at a 2U. Like I said, 64 ports are kind of the what we're leaning towards. NPU with 40 to 6.4T, again non-blocking, so there is no room for oversubscription in the fronthaul traffic. With an Intel processor and hot swappable fans. I think one thing I forgot to mention on the fronthaul gateway is, since it goes in the cell site, everything has to be front access. So your power supply, all of that would be front access. Okay. That's kind of what I have. So like I said, these two specs are work in progress. We're going through the design, and we're in the process of even selecting the silicon, the right options. So if you have additional use cases, so these are some of the use cases that we think AT&T would use. But if there are other use cases that this box can be used, you're welcome to provide that as a contribution. And also, if you have other requirements, I would be happy to include that in this requirement document. So I have the links for the specification, and appreciate feedback and involvement in this spec. Thank you. Any questions? Okay. Go ahead. I can give you the mic. Thank you.
So how close are you or AT&T to deploying this technology?
Meaning, like I said, we're developing the spec, right? So in terms of then, you would have to build a box and go through certification. So I would say at least we are at least a year out. If all goes well, we expect to do this maybe late part of next year.
Okay. Thank you.
Just a curious question from the fixed site guy.
Sure.
What kind of control plane is required for such a fronthaul access? That looks to me like something very static, point to point.
Yeah, I think we are not, on the NOS, I haven't talked about any of that, right? So it's basically going to be, like you said, it is static. So not much of, we don't expect that to be any different from what's today.
Okay, in that sense, if it's static and point-to-point only, why do you need such large x86 CPUs for control? Wouldn't that be a highly energy-efficient ARM use case?
Which meaning we are only doing like a four-core CPU.
Yeah, if you mount a 4-core CPU on a pole that does nothing.
No, on the
does
pole,
not feel really...
good question. On the pole, we actually don't think the 4-core would be the ARM is also a good option there. So that's one thing that we're looking at. On the pole, it's probably very lightweight. Right.
Okay,
Yes.
thank you.
There's one function, the DU, you have to load balance it from the CAS, or does it have to be a load balancer, and that's not specified yet, so.
Right. That's also work in progress with the ORAN group. So, because you wouldn't want to load share, right? Because when you do the DU pooling, you can have any radio connect to any DU. So that's going to be actually another algorithm that would be part of how you do the load sharing in the DU.
So that,
Yeah.
I think my suspicion is with that specified, that some kind of control, probably need some kind of switching mechanism. The protocol might change from static to dynamic, some kind of,
Well, that's a good point, but I think we're also working with the ORAN, depending on how they progress, right? Because it may actually be a little bit more sophisticated algorithm is what we are hearing recently. So that could also be part of the DU complex. So that's kind of yet to be, I guess, more to be explored in that area.
So whatever we
Yeah.
put in, we have to be able to kind of like adapt.
Right, especially on the CAS, yes. There are some, complexities there with the DU, because it would interface with your DU as well as, the traditional BBU, right? So I think the design would be a little bit more complex in the CRAN, whereas pretty straightforward in your fronthaul gateway at the cell site. There we want to keep it as simple as possible. Okay.
Anyone else?
Okay. Thanks for your time today. And